You open your laptop. You click one link. The page loads before you even blink. You don't think about it. Why would you? It feels instant, automatic, almost magical. But behind that single click, a war is happening. A war between every device in your house, fighting over an invisible highway made of radio waves. And the strange part is, that war is happening right now, even as you read this sentence, somewhere in a room near you. Your Wi-Fi router doesn't have wires for most of its traffic. It broadcasts. It shouts into thin air, using radio frequencies your eyes can never see. Every laptop, every phone, every smart bulb in your house is listening to the exact same shout, on the exact same frequency, at the exact same time. So how does any single device get a word in? This is where physics becomes politics. Imagine a room full of people who all want to talk, but only one person can speak at once without becoming noise. That's your 2.4 gigahertz or 5 gigahertz Wi-Fi band. It's a shared room, a crowded one. Engineers solved this decades ago with a protocol called CSMA/CA, Carrier Sense Multiple Access with Collision Avoidance. Translate that into plain English. Before your phone speaks, it listens first. It checks if the air is quiet. Only then does it transmit. But listening isn't enough. Two devices might check the air at the exact same microsecond, hear silence, and transmit together. Their signals collide. Garbage data. Wasted time. So your devices don't just listen. They wait a random, tiny amount of time before speaking, like two people who both went to say something at once, then pause, embarrassed, before one finally continues. That randomness isn't an accident. It's a deliberate design, baked into the firmware of nearly every wireless chip on Earth, preventing total chaos from 100 devices broadcasting at once. Here's where it gets faster than you can imagine. This entire negotiation, sensing the air, waiting, transmitting, listening again, happens in microseconds. Millionths of a second. Your brain hasn't even finished processing the word click before this invisible negotiation has already finished dozens of times. This idea of taking turns on a shared channel isn't new. It traces back to a project in Hawaii in the 1970s called LOHANet, one of the earliest networks built to let multiple radios share one frequency without a central operator managing every conversation. Modern Wi-Fi is a direct descendant of that experiment, refined for a world with far more devices and far less patience. And once a device finally gets to speak, what does it actually say? It doesn't send your whole web page at once. It breaks your request into small pieces called packets. This idea, breaking information into independent, addressed chunks instead of one continuous stream, is called packet switching. It was one of the most important shifts in computing history, born in the 1960s out of early networking research, replacing the older idea of a single dedicated wire reserved just for you, the way an old telephone call worked. Each packet carries a tiny header, a return address, a destination, a sequence number, so it can be reassembled correctly even if it doesn't arrive in order. Picture mailing 1,000 postcards instead of one long letter, each postcard numbered, addressed, sent independently, sometimes through different paths, but all expected to arrive and reassemble into your original message. Your router is the post office for this chaos. It receives packets from your modem, decides which device on your network each one belongs to using something called a MAC address, a unique fingerprint burned into every network device at the factory, and forwards the right packets to the right device, milliseconds apart, over and over, thousands of times per second. But radio waves aren't infinite. There's a hard ceiling to how much information can move through the air, no matter how clever the engineering gets. Have you ever wondered why adding more devices always seems to slow everyone down, even on a fast connection? This is where Claude Shannon enters the picture. In 1948, he proved something almost philosophical about information itself. Every communication channel, no matter how advanced, has a maximum capacity, limited by its bandwidth and the noise in the environment. We now call it the Shannon-Hartley theorem. It means your Wi-Fi isn't slow because of bad luck. It's slow because physics put a ceiling above it, and you happen to be sharing that ceiling with every microwave, every neighbor's router, and every Bluetooth speaker nearby. That's why moving your router, switching to the 5 GHz band, or reducing connected devices actually works. You're not improving your luck. You're shrinking the crowd of voices competing under the same hard limit. There's an even stranger problem hiding in this story. Two devices on opposite ends of your house might each sense silence near themselves, but never hear each other directly, separated by walls or distance. They transmit at the same time, confident the air is clear, and collide anyway, invisible to one another. Engineers call this the hidden node problem, and it's one of the quiet reasons your Wi-Fi sometimes stutters for no obvious reason at all. Why does your video call freeze the moment someone else starts streaming in another room? Now you know. They're not stealing your internet speed in some abstract sense. They're occupying physical airtime, actual microseconds of radio access, that your packets needed to sense the silence, wait their turn, and speak. When a packet doesn't arrive, or arrives corrupted, your device doesn't panic and give up. It waits for an acknowledgement. If none comes within a tiny timeout window, it resends, automatically, silently, often before you even notice anything was wrong. This retry mechanism is part of what makes the internet feel reliable, even though the underlying medium, invisible radio waves bouncing through your walls, is anything but reliable on its own. So every web page you load is really the final, polished result of thousands of tiny negotiations. Devices sensing silence, waiting their turn, splitting data into addressed fragments, racing each other through open air at the literal speed of light, governed by a mathematical ceiling discovered before color television even existed. None of this requires your attention. None of it requires your understanding. It simply happens every second, in every room with a router, whether anyone is watching or not. You open your laptop. You click one link. And somewhere between your fingertip and that page appearing, an invisible race has already finished 1,000 laps before you even noticed it had started.